Okay, to solve for the gain, the first, the most commonly used method is called deep convolutional gain. Okay, well, it's nothing but just go through. Especially for the generator, okay? Just go through a series of convolutional layer, okay? And then you get an output, and you input to the discriminator, okay? As I mentioned, see that originally it just generate one, the original version. It does not have to be 100, okay? But the original version of the code, it generates 100 random number from the standard Gaussian distribution. Well, actually, you should have MLP here. Well, actually, you should have an MLP here. 应该有一次 okay? The node. Okay, you have a Z1, Z2, and Z100. And then it goes through okay, the number of node is 4 times 4 times 1024. Okay, well, actually it usually goes like this. 好，就是100，然后呢，再经过一个好 hidden layer, okay, and the number of node is equal to 4 by 4 by 1024. Why is that? Because then we reshape, right? Then we reshape. Because this is 1D, then we reshape it into 2D. That becomes 4 by 4. Okay, the image size or the feature map is 4 by 4. The channel, the number of channel is 1024. Okay, that's the original version. And we go through a lot of convolution. Actually, you can replace this with VGG, that'll be fine, or anything that'll be fine. Okay, but you need to upscale it. Okay, upscale it, and generally the final size for the original case, the final image size is 64 by 64. Okay, that's it. Okay. Okay, so that's the original. Just use the convolutional. Okay. First, generate 100 random number. Okay, and go and pop up. Okay. So the first part here is the generator. Once you generate the image, then you go through the discriminator. Okay, okay. There's a series of the convolutional node, but there's one single output. Okay, once you use a CMOS. Okay, not some. Actually, you can use some max. That'll be fine. Okay, but you use CMOS, so the output value is either 1 or 0. Of course, it won't be 1, exactly 1 or 0, but very close. But the value is somewhere between 0 and 1. 这是原来的 VGG， 然后我们都把它当成是 convolution 来做。OK， 它是 called DC。OK， deep convolutional gain. Okay, that's original version. Okay, so as I mentioned, the first part is for generator, the second part is for the discriminator. Both are based on convolutional neural network. Okay? Okay, I already mentioned this. It converted the 1D, reshaped it into the size 4x4 by 1024. Okay? So this is the Hongyi, okay, from Taiwan University. This is a very good example. Okay, again, you just mentioned it. 100, then you go for this layer. Okay, this hidden layer. The size, the number of node is 4 times 4 times 1024. Okay, then you reshape to 4x4 by 1024, then it goes through upscale, okay, then you upscale to a series of convolution layer, namely this V5. So you might wonder, right, how come you can transfer all the meaningless random number into an image, right? That's because you need to give the target, okay? What will be the target you want to generate, okay? Okay, so that's, well, actually, nowadays, if you use GAN or any GAN variant, the model, we use this, okay? Versus thing, okay, let's say it's a German name, okay? That V, okay, versus thing, okay? It needs a lot of mathematical background, but the implementation is easy. Let me just show you the implementation. I will skip a lot of details. But anyway, here's our, that's the problem in the original, okay, objective function. We try to minimax, okay? We try to find the parameter that will maximize the discriminator. Then we try to find the parameter that will minimize the generator, but actually, you know, G and D, they are conflict to each other, okay? To each other. So first, if we take the problem as the game theory, then you can achieve the Nash equilibrium, okay? 这是那个纳什的平衡点，好，这个在这个竞赛理论标准的哈 ，OK。So it's very hard to converge. Okay, the first point. I didn't say it cannot converge. It's not easy to converge. And the other problem is you might get the variance gradient. The variance gradient when you use a backpropagation, the gradient might becomes 0. Okay, when the gradient becomes 0, right? That's the gradient equation. This is the rendering rate. This is the gradient when you, especially when you go through several convolution layer. This value becomes 0. When it becomes 0, there's nothing you can do. Okay, you will get stuck. Okay, right? Because you cannot improve your estimate or you try the parameters, okay? So that be the problem, okay? That be the problem. But if we go use the WGN, it will be bad, okay? It will be bad, okay? That's what I'm saying. This is the gradient. This is the gradient. Will be approach to 0. Okay, that's why the so-called gradient vanish. So which means the training failed. okay? And you will collapse, okay? It might collapse, okay? Which means you will always produce the same output, no matter what you do. So the diversity of the generated image is quite limited, okay? So here comes the W versus then distance. If you are interested, you can look for the detail. It uses the so-called Earth movers distance. Earth mover distance. The idea is you have a lot of pie of boxes, for example, okay? If you have, then you say how to move, okay, from the point of A and to the point of B, how to move it, so that there will have the same boxes, okay? You use a lot actually for the distribution. If you have one distribution like this, you have another distribution like this, then how to shift the distribution, the value, so that both will match to each other, okay? That's a very popular method called Earth movers distance, okay? And then you can prevent gradient vanish. We can skip the details. Whenever we try to match, for example, if this is the ground truth, okay, this is the ground truth distribution. And this is the observed. So for this case, of course, you know what? You have to move the observed distribution or estimate, or you estimate distribution so that both will match together. Okay, that's the idea. But for this case, it's fine. But if we have, during the optimization processing, this is the ground truth. This is the estimate. I say estimate the distribution A. And I may have another estimate the distribution called B here. Now, if we measure by the KL divergence or entropy, okay, if this code P, okay, and this code F, let me call it P, and the distribution we call it F1, and we call this F2, the distribution. Do you know which one is much closer to the ground truth? No, you don't. Based on the measure here, you say no matter it is a distribution F1 or F2, they are not similar. They are far away from the ground truth. But however, visually, it tells us what? F1 is much closer to the ground truth, right? So for the next gradient search, we know this escape. We can approach F1 gradually to the ground truth. You know what I'm saying? Okay, but for this case here, you cannot tell. Is F1 better or F2 better? No, you have no idea at all. 知道我意思吗？因为两个都离很远，可是离很远，里面还有一个离得比较近一点的，那我们应该从近一点的下手。可是呢，从传统的那个 gradient 的角度来看 ，you cannot tell the difference. So the Earth mover is just say we have two distribution. Then you simply measure the distance here. That's it. It's so simple. I mean, it has a very strict mathematical background. But anyway, the implementation is easy. You simply calculate the distance. Okay? So for this case here, you know F1 is much closer, right? It's much closer to the ground truth, right? If I put it D1, and then this is D2. Okay, the distance here we call it D2. So you know D1 seems better than D2, right? It's much closer. So that's it. That's it. Okay, so simple. We just based on the distance. Okay. So if for this case here, the distribution there, both are so far away from each other, you know, the KL divergence, okay, the KL relative entropy, actually the distance is infinite large, which means you cannot tell the difference as long as there's no overlap or partially overlap. Okay, so for the W, okay, Jian use Earth mover. Okay, simply calculate the distance. That's it. Okay, and here's another measure. If you want, you can take it off. Okay. Anyway, again, if the two distributions are so far away from each other, there's no overlap, then the value always log 2, which means the ground truth here, and here's another measure called J's measure. Here is log 2 is also log 2. Then again, you cannot tell F1 is much closer to the ground truth or F2 is far away from the ground truth. Okay, so anyway, it just simply calculate the distance. Okay, that's it. Okay, I will skip a little bit. Okay. Here's an algorithm if you want. Okay, it calculates the gradient. Okay, based on the W gain. Okay, W gain if you want. I will skip a lot of detail. This is how you update the gradient. Okay, how you update the gradient. But the distance as a measure is simply calculate the distance. Now, if in case you have a chance to write your own code, you will set up the clip, okay? W is the parameter value or the weight you want to estimate. The clip, it means what? It will limit this W value between negative C and positive C. You set up the clip, okay? So that you won't get too large or too small. OK， 好，这是一般在实物上，这个以后你有机会自己写的话，有时候会太大，那个值会太大。So 它这边呢算完以后它这个 this is gradient update, but it does not use adder, it use another method. But anyway, it will limit the output, the estimate parameter value between positive and negative C. Okay, that's something you can learn from it. 因为有时候你一下跑太大，整个会乱掉。它把它限制住。OK， 限制住。That's something you can learn from the algorithm here. Okay. Let me show you how the implementation with the code. Okay. The vanilla, when I say vanilla, you know what I mean, right? Whenever you read a paper, it says vanilla GN, which means is the basic model. The basic model. 就像你吃那个冰淇淋啊 Okay, when you have an ice cream, what is the basic flavor? It got to be 香草 right? It got to be vanilla. Okay, so you can have any others. Okay, here for the discriminator, I didn't say I don't need to say anything else. Okay, now for the discriminator, the output is sigmoid, right? As I mentioned, the output activity function is sigmoid, so that the output value will be between 0 and 1. Okay, that's the first thing. Okay, in the vanilla gain, but in the W gain, it didn't use, okay, see that, just return. It simply use the output, okay? It does not use sigmoid. It does not use sigmoid, okay? Because sigmoid will limit between 0 and 1. And in this case here, as I mentioned, when you estimate distribution for F1 or F2, you cannot tell the difference or how far it is away from the ground truth, okay? So the first, it drops the sigmoid, okay? The output is simply calculate this term, okay? This term. So that's the first thing for that, okay? It drop, see that? It just return the output value, okay? It doesn't convert the output value with sigmoid activation function, okay? So it's so simple, but it works. It works, okay? Now the next thing is about the other thing here, okay? For the vanilla game, first you will calculate the discriminator loss, okay? 损失函数啊，分类器的 Now you will take log, right? Remember, so you take log, and the other one is 1 minus, okay, the 1 minus d, then you take log. Remember that? Okay? 不是吗？啊，第一个我不是取 log 吗 ？d， 然后呢再减掉 d 减掉，不是吗？啊，不是吗？这样子，好 ，OK。对不起，我应该 pass. Okay, you will use a cross entropy. Okay, and now for the generator loss, again we take log. Okay, we take log. Okay. Now in W gain, take a look. It's simply reduce, just remove log. Okay, it didn't take log. It didn't based on the K or divergence. It simply calculate the distance. See that? It simply calculate the distance. Okay, 它直接算距离，它不知道取 log 啊。可是呢，效果就改善很多。It improved a lot. Okay, it simplified the standard or the vanilla gain, okay, just by drop the sigmoid, by dropping the log function or the KL function, but it uses earth mover, which is simply calculate the distance. See that? It simply calculate the distance, okay? And also it's the same for the generator loss, okay? It drop log. That's it. That's all you do, okay? And so when you have a chance to run your game, you need to watch out does the model use WGAN to solve for the problem or not? Okay, it's much more efficient and effective. Okay, and it can try eliminate the gradient vanish. Okay, and the training will be more stable. Okay, usually when you train the GAN, it's not stable at all. Okay. And I can even say it's very hard to train. Okay. Okay, so that's about GAN. Any question? 好，这是 GAN 标准的，也很聪明哦。Okay, right? It designed a discriminator and generator. Okay, so that they can find each other. Okay, so eventually, it will make the make the generator create an image like the real one. Okay. Okay. If you have no question, let's go further. Then there's a lot of different versions. Okay. I just introduced some very popular and some very easy to implement. Okay, for your own application. You can use it just so for you. Your research work, or even when you work for some company after you graduate, this always something you can use. It does not have to find some very fancy one. Okay. This is called conditional GAN. Okay, GAN. Okay, you can find the code from public library. When you say condition, means I set up the condition. Okay, when I try to generate the image, it must under some constraint, under some condition. So here's, as I mentioned, for the generator, the vanilla model of GAN, first you will create random noise, right? By following uniform distribution or Gaussian distribution now, but it puts some constraint right here. See that? Not only input the random noise Z, but it also input the condition. Okay, the condition. And the condition not only for generator, but also for the discriminator. You need to input both. And all the remaining part will be the same. Okay, the generator will try to create the image look like the real one. And the discriminator try to identify the real image and the fake image, no matter how similar of the fake image generated from the discriminator. Okay, so that's the idea. Just put the condition. Now, this is original GAN loss function here. Okay, we try to minimax. Okay, here's the condition. You won't see anything different here, but you can see the probability is here. It's given what? Okay, given what? Why is it given? Usually it's user specified. 就使用者你可以设定它的条件是什么。And then everything will be the same. Okay, this is the random number, right? And this is the generator with the input Z. Also given the condition 1. Also given the condition 1. Okay? That's the only difference. Okay, only difference with the additional condition. Okay? So as I mentioned, it's still a minimax. But I need to emphasize again, if we think of the discriminator, this is the equation, include the second term. But when you try to find the minimum loss function for G, it's still based on the second term. See that? still based on this. So you need to struggle between D and G, okay? In each iteration, right? You know what I'm saying? 你说你要找到一个最好的 D， 可以呢一下子分辨它是真的还是假的。可是呢，你设定好那个值，把它定住以后呢，你又希望这个 G 呢能够让它越像越好。Right? You try to maximum, which means you need to what? You need to make the output exactly to be 1. But for D, this term should be 0. Right? 它要是0哦，这一项哦，要是0哦，就 discriminate， 因为它知道是假的哦，它要是0。可是呢，当你训练好这个 D 的所使用的参数的时候呢，那你有期待这个 G 可以让这个 output 的值呢变成1。Oops， 它不是两个是矛盾哦，所以为什么它两个在一起挣扎？好 ，they have to struggle, okay, between these two terms. Okay, here's some example for the conditional gain. Okay. This is much easier to understand. First, we input a sketch. Besides the render noise, we just give the sketch, and here's the output. Okay, you will make a real purse. Okay, a leather purse, or we input something like this, then you will convert into a map. Okay. Or just give it something, and then you will convert it into a building. Okay. Okay. So that's the condition we input. So actually, the condition Y can be an image. It can be a vector, value, data. You know what I'm saying? You can input Z, or you can input vector value. For example, the output of the generator could be a face. So Y could be, the Y can be 0 and 25. It means that the face you are going to generate, 0 could be female. It cannot be a female. And the age is 25. So the generator cannot be any face. Okay? It must be a female. And the age should be around 25. If you don't provide this information, then it could be randomly generate a face. It could be a man, right? Or it could be an older lady. So why? So the condition can be an image, or it can even a sentence, okay, a text, or a vector value. So this is called the conditional gain, so that you can control the output that you are looking for, okay. Okay, so that's it. Okay, just put the conditional gain. The only thing you need to put, just put it here. Okay, just put it here. Okay. Here's an example. Here's an example. The conditional gain architecture. See that you input the 100-dimensional random vector Z, and then you put 10 dimensional 1/2 level. Apparently, the task here is try to generate the handwritten digits. Okay, handwritten 这是手写字。Okay, we have a 10 digit 0, 1, 2. So 0, 1, 2, 3. So apparently you want to generate 3. Okay, want to generate 3. So you put this 1/2 encoding, you take it as an additional condition. And then this 100 and this 10 one hot encoding, then you concatenate together. So the dimension will become what? 110. OK? 100，因为你做串接嘛，会把那100个随机乱数再加上这10个，把它串接在一起。So the dimension, this 100 dimension z vector plus this 100 random one hot encoding, so the length will becomes 110. And then you find the dense, okay, convert it into the size, and the number of nodes is 7 times 7 times 128, and we reshape it to 7 by 7 by 128, and so on and so forth. Okay, so the idea is here, we put the concatenation, okay? And then it just goes through convolution. It uses a transpose convolution, upsample, okay, upsample. Okay, and that's it, right? And it generates 3. That's why 3, that's because we asked. We set up the condition, right? The one hot encoding represent the digit 3. Okay? And here, this for the discriminator. Okay, you will include the input, the fake, okay, handwritten digit 3, and also you need to input the one hot encoding, okay, here. And then we do the concatenation again. That goes through a series of convolution. And then finally, we use a simoid as activation function because the output is only one node. Well, actually, it can be max, that'd be fine, okay? But you use a simoid, okay? So this is just a simple example how we set up the condition here, okay? The condition here is digit, okay? It's digit. So that we can make sure the output is 3, but not anything else, okay? Okay, any question? Okay, condition? Let me show you one more, okay? It's very useful, especially when you work for if you have some manufacturing or when you do some classification, but if you don't have enough training data set, okay? Especially about the defect, because you might only have a few. The defect, okay, sample for each time. This is something you can do. It called pixel to pixel, okay? PIX, 2 means 2, PO. Pixel to pixel. This is for image to image translation, okay? Image to image translation based on conditional gain, okay? So it can download this model. It's based on my own experience. It is very useful, okay? It's very useful because you can set up the condition you want, okay? You can manipulate manually, okay? By set up the condition. Okay, here's example, okay? Here's the condition. Here's the condition, okay? The sketch of a book. OK， 那个鞋子啊，那个靴子，你用素描把它画出来。And we input a generator, right? We just do the decoding, and we generate the book. Okay, actually it's fake, but it should look like the sketch here. And also the generated image and the condition, which is the sketch. We input those into the discriminator. And then the output should be fake because it's generated from the generator. okay? But again, for the discriminator, we input a real picture of the booth and the hand drawing, or you can actually input as what? As an age detection, by age detection. 不是吗？你可以用 edge detection. Then we input it to the discriminator, and the output should be 1. Okay, should be 1. That's something you can do here. Okay, so you can input, okay, X sketch. Okay. Now you might wonder if the input is Z. How can I input Z and X? You might use autoencoder first. Okay? You input the hand drawing booth, okay? The sketch of booth, right? And then, okay, you can catch the Latin variable and concatenate it with the random number. Okay, then there's another way you can do this thing. Okay, or not. If you input, anyway, you can input the random. As I mentioned, well, where is? Let me find. Wait for me. Oh, right here. Okay. Generally 100. Okay, dimensional random number. Then you can put. Then you can put this value. Okay. You can do the concatenation here. Okay. Okay. You can put it here. To concatenate, to extend the dimension. Okay, there's another way to do the conditional. Okay. So pixel to pixel, okay, a very useful model that can create something you want. Okay, you can have a control of the possible output. Okay, the pixel to pixel. So that's the idea. Okay. And the loss function, basically the loss function for the pixel to pixel, okay, for image to image translation, again, okay, minimax GMD. That's the standard Gauss GN. Then the plus L1G, the generator L1, okay. So it put another term. This is so-called regularization. Okay, lambda. The lambda value does not have to be 0 and 1. It depends how do you want to emphasize to the conditional gain or the L1 loss. Okay, so the conditional gain is nothing but just like the regular gain. Okay, but L1. You try to minimize, you use a mean square error, okay, try to minimize the difference, okay, of the generator and the something you expected, the one, okay, the one here, just like you have to make sure the one, okay, the one here, okay, the ground truth, okay, the ground truth. Image, okay? So besides the regular gain loss function, it adds something, try to minimize the mean square error for the generated image and the ground truth image, Okay, so that's it. And you need to carefully regularize or adjust this this term. Okay, you can think of this as a regularization term, lambda. Okay, as I can mention, it does not have to be 0, between 0 and 1. Okay, it does not have to. It could be 10 or even 100. Well, you need to try out. Okay. Okay, you put 1 here, it means you use absolute difference of L1. This is 算绝对值了. If I put 2 here, it means the mean square error. Okay, you need to know how to read the mathematical equation. Okay, 1 here is L1. Okay, L1. 这是算绝对值。假如这边放 2 的话呢，就是算它的平方差。Okay, okay, that's conditional. Okay, the conditional. Some model even use the UNet. Okay, you have familiar after your assignment number 5. You use UNet, okay, as the generator, so we can input X. So if we use UNet as the generator, which means the input does not have to be random number. The input can be an image. The input can be an image. 好不好？假如你用 UNet 当成是它的 generator 的话，你不需要一定要用随机乱数当成输入，你就直接输入一个影像。Okay. And then this case is much more like image to image translator. Okay. You want to translate, as I just mentioned, translate a sketch into an oil painting. 把素描转成油画，那这个你就可以用 ，OK， 你可以输入素描，那个就不需要用到前面的 conditional 这样 it simply just replace the generator with a unit. Okay, so the input, of course, it can be a random number, but most of the time when you apply unit, the input could be an image. Okay, could be an image. Okay. So this encoding, that's a variable and decoder, and then this is output synthesized image. But this you still need input this to the discriminator, and hopefully the output of the symbol value should be 0. Okay, so that's something you need to learn. And with the additional regularization term could be something like this. Okay, could be something like this for UNet. Okay, for UNet. Okay, so that's pixel to pixel or conditional gain. Okay. I put a note here. Okay, because someone, especially for the conditional gain or UNet, some people try out. What if I don't use the random noise Z? What would happen? You can go read it just by yourself. If the original author found out Z may not be necessary, it won't help. Okay, with or without this. I didn't mean the original gain. Okay, the conditional gain or the one with UNet. Okay, with UNet. It says it makes some experiment with or without the random number vector Z. It didn't find it. It may not help. Okay. So anyway, you can take it just for your reference. Okay. It may not be true for your own application. Okay, but for most of the case, apparently for the conditional gain, the random variable Z is not necessary. Okay, as you say, it's not necessary. Okay, but just based on the author's experiment. Okay, let's take a break.